Okay, in this video we're going to go through 3G of the notes, which is going to be Newton's first law. So this is the last of the three laws. So we've talked about the second, we've talked about the third, now we're talking about the first. So the first law, there's a couple concepts before we actually get into the full wording of the law. The first is inertia. So inertia is the property of an object to resist changes in motion. And changes in motion really are acceleration. So remember that acceleration is a change in speed and or it's a change in direction. So again, if you're seeing changes in motion, that's really an example of acceleration. The other concept that we need to think about is mass. So again, mass, very familiar at this point. Mass is a measure of inertia. So if you have more mass, you have more inertia. If an object is more massive, it's going to have more inertia. It's going to be harder to change its motion. So again, if you have like a tiny pebble, its mass is pretty small. Its inertia is also going to be small. It's going to be easy to move that around to, speed it up, slow it down, move in different directions. That opposed to if you had like a big rock like this. If the mass was higher, it's going to have a higher inertia. This is going to be more difficult to move around. Right? Newton's first law, and we can get to the actual wording of the first law, describes an object's tendencies to change their motion. So again, it's a very broad, kind of more conceptual law, but it is useful. It does actually describe a lot of different things. So right here is the fairly official wording of the law. So an object at rest tends to stay at rest, and an object in motion tends to stay in motion unless the object is acted upon by a net force. So there's different ways of thinking about that. One way I like to think about that is it's effectively saying objects are lazy. Objects are lazy. Again, when I mean, it's a little bit of personification, but when I mean objects are lazy, it's basically saying that, they're going to do whatever they were doing before unless something forces them to do otherwise. So if something's sitting still, I'll write that out here. If you have like a sphere, I don't know, sphere standing still, and there's nothing acting on it, it's just going to stay still. If you have a sphere that's moving, it's going to stay moving unless something actually comes along and makes it stop or change direction. So again, it's saying if there's no net force, if there's nothing forcing an object to change, then it's going to do whatever type of motion it was doing before. If it's at rest, it'll stay at rest. It's moving, it's going to be moving, and again, moving in the same direction at the same speed. So that's the first law. That's the kind of official wording of the first law. So there's a couple kind of subtleties to it that are good to point out right here. So if an object has no net force on it, by Newton's second law, it also has no acceleration. So again, we've actually seen this in previous sections, but it's good to go back, think about it again. So if there's no net force in an object, so again, if there's either no forces or they cancel out to zero, that really means you have no acceleration. And if there's no net force, an object's not accelerating. And if an object is not accelerating, right, there's no net force on it's not accelerating, it's going to be moving at a constant velocity. And it's important to remember what constant velocity means. Constant velocity means that it's not changing its velocity. And that velocity could be, I don't know, it could be 0 meters a second technically, because 0 would be a constant velocity. This would be a constant 0 velocity. So if it's not moving, it's not accelerating, there's no net force on it. It could be 5 meters a second would be a constant velocity. It could be, I don't know, 1,000 meters a second. That's really what this is saying. So again, if there's no net force, there's no acceleration, and then the velocity is going to be constant. And that constant velocity could include, 0. It could be 0 technically. And the last thing right here is very important. So again, this is, you might be thinking, okay, first law, great, seems to make sense. This is actually, it's hard to actually observe this on Earth. So again, the reason most objects on Earth come to a stop is that friction and air resistance are exerting a net force on them. So if we think about it, Newton's first law says, oh, well, if it's moving, it should keep moving. That's right, but on Earth, most stuff, there's really nothing that's going to keep moving forever. I don't know, eventually if something's moving, give it enough time, it's going to come to a stop later. So again, the reason we have, second law is a little bit tricky is because on Earth there's almost always net forces acting on objects. And those two net forces are going to be friction and they're going to be air resistance. So again, if you look at the free body diagram of this ball that I drew here, if it was moving, it's eventually going to come to a stop, and that's because there is a net force. In this case, we'd be worried about friction. We might also be worried about air resistance, depends on the situation. So your net force is not going to be zero on Earth very often. So again, in space, this first law would make be a lot more intuitive. You throw something, it'll keep moving. Something's just sitting there, it's going to keep sitting there. But on Earth, we have to remember there's very often friction and air resistance that are going to cause things that are moving to come to a stop. So that was the first law. As you probably noticed, it's very conceptual. There's not a whole lot of math in it so far. But it is important. It does describe a lot of different things. Okay, last thing we're going to do is we're going to do an example out of the first law. So this is an example of a first law problem. So again, before I go through it, before you see the solution, make sure you read it, go back through the notes, make sure you take an attempt at solving it. So again, make sure you take an attempt to solve it. You're not watching Vine videos. Okay, let's go through it. So what do we have here? We have a soccer ball with a known mass is moving at 2 meters a second across frictionless ice. How much force is required to keep the ball moving at that 2 meters a second? So we're looking for force. So let's think about it for a second. So again, there's no friction. We can assume there's no air resistance unless it says otherwise too. So the answer to this is actually going to be 0 newtons. And I'll explain why in a second. So the reason it's 0 newtons, there's no force required, is because if we remember Newton's first law, again, Newton's first law, what it states, objects in motion tend to stay in motion, and I'm just going to abbreviate a little bit, but objects in motion tend to stay in motion, objects at rest tend to stay at rest unless acted on by an outside force. So there's no net force here, really. It says there's no friction. We're going to assume there's no air resistance, unless it's specified, explicitly there was air resistance. So again, there's no net force, and it's moving at 2 meters a second. So how much, force is it going to take to keep it moving at that rate? No force. Again, if there's no net force, that object is going to be lazy. It's going to keep doing what it was doing before. So again, it was moving at 2 meters a second. You look at it, a day later, it's assuming it didn't run into anything, it's still going to be moving at 2 meters a second. Providing, didn't hit anything and there's no introduction of force. So again, because there's no net force, Newton's law, first law, says there's no force required to actually keep it at that rate. So that's the problem. So again, you've seen the notes, we've seen an example problem. Make sure your notes are notated, make sure you have this problem down, And that's it for now.